Hello, my dear student. Welcome to EPG Pathshala. I am Anchal Srivastava from Department of Physics, Institute of Science, Banaras Hindu University. Today, we are going to talk on the module titled Basic Properties of Nanoparticle 2 under the paper Nanoscience and Technology 2. After completing this module, the student will be able to learn the classification and 0D, 1D, 2D and 3D materials. D signifies that dimension. So, 0-dimensional, 1-dimensional, 2-dimensional and 3-dimensional materials. Quantum confinement and energy expression in K space. Fermi energy and Fermi function for electron gas. Expression of the density if states for 0D, 1D, 2D and 3D material and their schematic representation. One of the most direct effect of reducing the size of the material to the nanometer range is appearance of the quantization effect due to the confinement of the movement of electron. This leads to discrete energy levels depending on the size of the structure, as it is known from the simple potential well treated in introductory quantum mechanics. Following this line, artificial structures with properties different from those of corresponding bulk material can be created. Control over dimensions as well as composition of structures thus makes it possible to tailor material properties to a specific application. Both semiconductors and metal nanostructure have been investigated over the years. While the application of metal nanostructure are still very limited, semiconductor electronic and optoelectronic components based on the structure with quantum size effect has been on the market for several years. The present note will therefore treat the size effect with semiconductor materials like gallium arsenide in mind. It is very rare that the nanostructures appear as freestanding structures. Rather, they are embedded in the matrix material that necessarily has an effect on the electronic level in nanostructure. In the rather simple treatments presented here, it is not possible to take the matrix materials into account. However, the simple models still give good impressions to the basic principle behind quantum size effect in various structures. The nanostructures treated here can be divided into the following classes. It should be noted that many applications of nanostructure do not depend directly on size effect on electronic property. Instead, the surface to volume ratio may lead to new functionalities. For instance, in catalytic effect, intensive research is directed towards introduction of new functionalities to matrix material without affecting other materials property by introduction of nano-size structures. We will discuss the classification of the nanomaterials based upon their size and dimensionality. Based on the size and dimensionality, the nanomaterials can be classified into 4 parts. The first one is zero-dimensional nanostructure. The second one is one-dimensional nanostructure 1D. The third one is two-dimensional nanostructure 2D. And the fourth and the final one is three-dimensional nanostructure. The three-dimensional nanostructure are the bulk nanostructures where they behave classically, whereas in first, second and third, where 0, 1 or two-dimensional nanostructure behaves quantum mechanically. Let us discuss the zero-dimensional objects. Usual names are nanoparticles, in this case, clusters, colloids, nanocrystals and fullerenes. They are composed of several tens to a few hundred atoms. Electrons in this case are confined in all 3 directions. This is clearly visible in figure. Let us talk about one-dimensional object. A cylinder-like object like wire or tube with diameter on the nanoscale and length typically in micrometer range is the example of one-dimensional object. Carbon nanotube is one of the example in this case. Also, embedded structure with rectangular cross-section exist. Confinement effects for electron may appear in transfer direction while electrons are free to move in one dimension along the length, which is shown in the figure clearly. Now, let us talk about two-dimensional object. This is a kind of film. This thin film with thickness of the order of few nanometer are usually deposited on a bulk material. Their properties may be dominated by surface and interface effect, or they may reflect the confinement of electron in the direction perpendicular to the film, like a quantum well. In the two-dimensional parallel to the film, the electron behave like a bulk material. Graphene or other 2D materials are the best example for this two-dimensional object, where electrons are free to move only on the film thickness on the film of the graphene surface. However, perpendicular to that, the electron movement are restricted. Let us talk the three-dimensional object. It is composed of several nanostructures crystalline expanding in all 3 dimensions. An electron can move in all directions, and in this case these materials behave classically. In this slide, I want to discuss the properties of this 0D, 1D and 2D nanomaterials. 0D nanostructures. In this case, motion of electron is confined in all the 3 dimensions. Therefore, electron is restricted in all the 3 directions to move. Examples of 0D nanostructures are the nanoparticles and the quantum dots. Now let us discuss 1D nanostructure. For one-dimensional nanostructure, electron will be free in one direction to move, while its motion will be restricted in remaining two directions. The examples of such kind of nanostructures are nanorods, nanotubes, nanofibers, etc. of different material. 2D nanostructure. In this case, the motion of the electron is restricted in only one direction and rest of the two are free. Then the nanostructure are called 2D nanostructure. Example of such kind of nanostructures are thin film, nanosheets, graphene, two-dimensional MOS2, WS2 and other material. Let us talk about 3D bulk structure. The 3D bulk structure contains features on the nanoscale including nanocomposite, nanocrystalline materials, nanostructure films, nanotextured surface, nanoporous materials and nanofoam. Sometimes considered nanostructure but not nanomaterials because only the wires and not the material themselves are on nanoscale. I want to talk about quantum effect. Nanotechnology as an emerging technology which has gained fame in every field of life, from an excellent sunscreen to an electronic chip. This emerging technology has given excellent properties to even those elements which at one time were thought to be being useless. For example, carbon is non-metal, but when considered at nanoscale, the carbon nanotubes are the best conductors. But what is the enigma beyond size if this size can make a non-conductor an insulator? What is the basic physics beyond it? Well, the answer is simple, and that is quantum confinement. The quantum confinement effect is observed when the size of the particle is too small to be comparable to the wavelength of the electron. To understand this effect, we break the word like quantum and confinement. The word confinement means to confine the motion of randomly moving electron, to restrict its motion in specific energy levels, which is called discreteness. And quantum reflects the atomic realm of particle. So, as the size of the particle decreases, we can reach a nanoscale. Decrease in confining dimensions make the energy level discrete, and this increases or widened up the band gap, and ultimately the band gap energy also increases. Since the band gap and wavelength are inversely related to each other, the wavelength decreases and decrease in the size, and the proof is the emission of blue radiation. For 0D nanostructure, all the three directions are quantum mechanically confined. In 1D, two directions suffer quantum confinement, and for 2D nanostructure, one-dimensional direction is quantum confined. Where I want to talk about electron confinement again. As we have discussed the quantum confinement of nanostructures in the previous slide, this quantum confinement is observed for the conduction electron. For 0D electron of the nanostructure are confined in all the three directions. Motion of electron is confined into direction for 1D nanostructure. For 2D nanostructure, the motion of electron is confined in one direction. Similarly, for 3D nanostructure, electrons are not confined in any direction. They are free to move in all the directions. The electron of confinement can be understood by considering this case of particle in a box problem. Now, I want to discuss the energy because of this confinement. Confinement of electron can be understood by considering the particle in a box problem in 0D, 1D and 2D. The calculated energy for 0D is En is equal to h square by 8 pi L square nx square plus ny square plus nz square. This has already been solved in quantum mechanical classes. For 1D, this equation changes and En is equal to h square by 8 m L square nx square plus ny square. And for 2D, this equation turns out to be En is equal to h square plus 8 ml square nx square. From here, we can conclude that the smaller the dimension of the nanostructure, the smaller the length, the wider is the separation between the energy level, leading to a spectrum of discrete energy. When particle size of solid matter in the visible scale are compared to what can be seen in a regular optical microscope, there is little difference in the properties of the particle. But when particles are created with the dimensions about 1 to 100 nanometer, where the particle can be seen only with a powerful specialized microscope, the material property changes significantly from those at larger scale. This is the size scale where so-called quantum effect rule the behavior and properties of particles. Properties of materials are size dependent in this scale range. Thus, when particle size is made up to a nanoscale, properties such as melting point, fluorescence, electrical conductivity, magnetic permeability, chemical reactivity changes as a function of size of the particle. Nanoscale gold illustrate the unique property that occur at nanoscale. Nanoscale gold particles are not the yellow color with which we are familiar. Nanoscale gold can appear red or purple in color. At the nanoscale, the motion of gold electrons is confined because this movement is restricted. Gold nanoparticles react differently with light compared to the larger scale gold particles. Their size and optical properties can put to the practical use. Nanoscale gold particles selectively accumulate in tumors where they can enable both precise imaging and targeted laser destruction of the tumor by means that avoid harming healthy cells. Where I want to discuss the Fermi energy concept. The Fermi energy is a concept quantum mechanics usually referring to the energy differences between the highest and the lowest occupied single particle state in quantum system of non-interacting fermions at absolute zero temperature. In a Fermi gas, the lowest occupied state is taken to have zero kinetic energy, whereas in a metal, the lowest occupied state is typically taken to mean the bottom of the conduction band. The Fermi function gives the probability that a given available electron energy state will be occupied at a given temperature. The Fermi function comes from the Fermi-Dirac statistics and has the form Fe is equal to 1 upon e to the power e minus ef by kt plus 1, which we have studied in our BSc classes. The basic nature of this function dictates that at ordinary temperature, most of the level up to the Fermi level EF are filled, and relatively few electrons have energy above the Fermi levels. The Fermi level is on the order of electron volt, for example 7 electron volt for copper, whereas the thermal energy kT is only about 0.026 electron volt at room temperature. If you put these numbers into the Fermi function at ordinary temperature, you find that its value is essentially 1 up to Fermi level and rapidly approaches 0 above it. Let us discuss the density of state. The density of state, DOS, is essentially the number of different states at a particular energy level that electrons are allowed to occupy. For example, the number of electron states per unit volume per unit energy. Bulk properties such as specific heat, paramagnetic susceptibility, and other transport phenomena of conductive solid depends on this function. Before going for the semiconductor statistics, one should know about their density of state. For 3D nanostructure, density of state is directly proportional to the square root of energy. For 2D nanostructure, it is independent of energy. For 1D nanostructure, it is inversely proportional to the square root of energy, and for 0D nanostructure, it is a delta function. I want to talk about degree of freedom, dispersion, which is the kinetic energy, density of state, and effective density of state for different materials. If I talk about the bulk material, which degree of freedom is 3, in this case, the kinetic energy expression is E equal to h square by 8m bracket kx square plus ky square plus kz square. And density of state in this bulk system is 1 by 2 pi square in bracket 8m pi square by h square to the power 3 by 2 under root E minus EC. And the effective density of state is written as 1 by under root 2 in bracket 4 pi m kt by h square to the power 3 by 2. When I reduce the dimensionality and come at 2D system like graphene or MOS2 or WS2 single layer films, in that case the dispersion kinetic energy is written as E equal to h square by 8m kx square plus ky square, whereas the density of state DOS is 4 pi m by h square E minus EC, and the effective density of state is 4 pi m kt by h square. If the same thing we want to figure out in case of quantum wire, where the degree of freedom is 1, in that case the dispersion kinetic energy E is equal to h square by 8m kx square. However, the density of state is 2m by h under root m by 2 E minus EC, and the effective density of state is 2 pi m kt by h square. And in case of quantum dot, where the degree of freedom is 0, the dispersion kinetics known, whereas the density of state is 2 sigma E minus EC, and the effective density of state is 2. For 3D nanostructure, density of state is directly proportional to the square root of energy. For 2D nanostructure, it is independent of energy. For 1D nanostructure, it is inversely proportional to the square root of energy, and for 0D nanostructure, it is a delta function. So this density of state is more clearly shown in this figure with a graphical representation of 3D, 2D, 1D and 0D material. So student, let us see what we are going to learn in this module. Depending upon the quantum confinement of the electron in nanostructure can be of 0D, 1D, 2D and 3D. The energies of 0D, 1D, 2D and 3D in K space is given by En is equal to h square 8 ml square nx square plus ny square plus nz square. The second one, En is h square by 8 ml square nx square by plus ny square, and En h square by 8 ml square nx square. Distribution of electron in a solid is governed by the Fermi function f, which is given as f equal to 1 upon e to the power e minus ef by kt plus 1. Density of state for 3D, 2D and 1D is directly proportional to under root e to the power 0 and 1 by under root e respectively. Thank you.